All right, let's talk about magnetism. For so many of us, this is the chapter where things get complicated, where you feel like you're losing easy marks. But what if there was a way to completely flip that around? Today, we're not just going to study magnetism, we're going to build a weapon to absolutely conquer it. Does this sound familiar? You've solved a ton of problems, you think you know the formulas, but when you get that exam paper back, the score just doesn't match the effort you put in. You are definitely not alone. But the crazy thing is, the reason why is usually hiding in plain sight. Okay, here it is. This is the insight that changes the whole game. In a lot of competitive exams, a huge chunk of your marks, we're talking up to 40%, doesn't come from the super tricky numerical problems you've been grinding on. Nope, it comes from the one thing that almost everyone skips. That's it. Core theoretical derivations. Yeah, the very things most of us look at and think, that's just theory, I'll skip it. This is the single biggest leak in most students' preparation, and today, we are going to patch it up for good. So, how are we going to do it? We're going to use a framework I call the theory bridge. Just think of it like a repeatable recipe, a system that connects a basic fundamental law to a final exam-ready result. This is the weapon you'll use to take down any derivation they can throw at you. And here's the code. It's so simple. Pretty much every major derivation in magnetism can be broken down into these 5 steps. First, you state the starting law. Second, you figure out the geometry and use symmetry to make your life easier. Third, you do the math. It's usually an integration. Fourth, and this is so important, you box your final result. Examiners are literally looking for that box. And finally, you just state what it all means in the real world. Okay, theory is one thing, but let's see this weapon in action. We're going to break down one of the most important derivations out there, finding the magnetic field on the axis of a current loop. You see this one pop up on exams all the time. Step 1, we state our starting point, our ground zero. And for this, it's the Biot-Savart law. This is our fundamental truth. It tells us the little bit of magnetic field, dB, that comes from a tiny piece of wire, dl, carrying a current. Every derivation has a starting line you cannot cross, and for the circular loop, this is it. Now, step 2, this is where the real magic happens. Geometry and symmetry. Just picture the loop from the side. For every tiny bit of current at the top of the loop creating a field, there's a perfect match at the bottom. And guess what? Their up and down field components cancel each other out. They're gone. The only thing that's left is the part of the field pointing straight down the axis. This insight is huge, because it means our problem just got way, way simpler. Step 3 is the integration. Now, don't let the calculus scare you. All we're doing here, conceptually, is just adding up all those little axial field components, the dBx parts, from every single piece of wire all the way around the loop. That's it. We're just summing it all up to get the total field, Bx. And after that integration, we land at step 4, the boxed result. You need to lock this formula into your memory. This is the prize. This expression gives you the magnetic field at any distance x along the axis of a loop with radius r carrying current I. So why on earth did we just go through all that? Because it lets you solve problems with absolute confidence. Let's take a look at an actual question from our quiz material, question 10b. It asks for the magnetic field right smack in the center of a coil and gives us the radius and current. Now, because we actually understand where our big formula came from, we know that at the center just means we set x equal to 0. And watch what happens. That big, scary formula instantly collapses into this beautiful, simple one. B equals mu naught I over 2r. You just plug in the numbers and you've got the answer in less than 30 seconds. That is the power of the theory bridge. Full marks, 0 guesswork. Okay, mastering the derivations, that's your offense. Now we have to build your defense. And that means learning to spot and dodge the most common traps that examiners love to set for students who aren't prepared. Knowing these is just as critical as knowing the formulas themselves. Let's run through a few of the greatest hits. For a solenoid, it is so easy to see the total turns n in the question and just plug it in. But the formula needs n, which is turns per meter. Big difference. For torque, it's that classic sine versus cosine mix-up. People forget it depends on the angle between the magnetic moment and the field. And for parallel wires, oh, that little 2 pi in the bottom of the fraction. It's so easy to forget when you're under pressure. You need to know these, check for them, and never, ever fall for them again. And finally, let's put this all together into a killer pre-exam ritual. This is a 15-minute drill you can do right before you walk into the exam hall. It's designed to get your brain primed and ready for peak performance.
So here's the drill. First, actively recall your top formulas. Don't just read them, pull them from your memory. Second, mentally picture the differences between di, para, and ferromagnetic materials. Third, quickly scan that checklist of common traps we just talked about. Fourth, flip through those key box results from your derivations in your mind. And last, just double-check the constants you know you're going to need. This isn't about cramming, it's about bringing all your sharpest knowledge right to the front of your mind right when it matters most.
Look, the most important takeaway here is this. Practice is just doing problems over and over. Preparation is about building a system. By weaponizing theory, by mastering these derivations, and by knowing the common traps, you're not just another student who practiced. You are a student who is truly prepared. Now go get those marks.